Hello. Today we are going to talk about circle theorem 2, and in this video we are going to analyze various areas that will be a continuation of what we did in circle theorem 1. So in this case then, before we continue, kindly like the video and subscribe. Now let's see the objective of this day. We are going to do exploration, and the first thing we are going to determine is the characteristics of internally intersecting chords, and secondly we are going to check the externally intersecting chords, which we are going to call them seconds. Thirdly, we are going to also check another externally intersecting the lines, which we call tangents. But in the second case, we can also talk about the secant and the tangent. We can combine the two there. So we have those three parts that we are going to do exploration in for today's particular video. So let's start. So let's start with internally intersecting chord. So let's demonstrate here and find out through investigation what really happens when we have internally intersecting chords. So let me just have it down here, just slightly down. Let me just enlarge it so that it becomes a bit sizable. Now, when we have internally intersecting chord, as I'm going to explain, let's just have this beautiful example here. You can see that there is an intersection in between. You see, there is an intersection of chords here, and what we are going to do, we are going to make sure that they intersect at a point, So what are we supposed to investigate here? I want investigation to be as follows. One, I'm going to pick the following lines, and then find their relationship. One, if we get the first test here, we take C, you can see the line CF. If CF is multiplied by FB, and then the second one, if EF, you can see EF is multiplied by FE, what are we going to get? Will it give us some insight on something? So let's get the dimensions of those particular areas. For instance, EF there is 3.493. I have EF there. I have also 5.2, that is FB, and then finally we have FD, which is 6.749. Now let us demonstrate them here. Now what I have is SCF times FB. CF, as you can see here, CF is 3.493. So let me multiply it by FB, which is 5, as you can see there, 5.254. What do I get here? That is the first part. Let me also take the second portion and multiply 2.719, which is EF, then multiply it by 6.749. What do we get in the two scenario? So when you multiply the two, I'm getting that the first part, that is CF times FB, you get 18.35. Then EF times FE, you get 18.35. Then there is something it is telling us. There is a relationship. So what is the relationship then? Can we talk about this particular situation? What is the relationship then? So the relationship here is very simple. So we can just say that CF then, CF, when you have CF times FB is equals to EF times FE. You see? Very simple. CF times FB is equals to EF times FE. So that is the relationship. In other words, if I can label this part as A, I label this one as B, the length of that line, and then C, and then D, then I can say that A times B is equals to C times D. So internally, intersecting chords have this particular relationship. That is one. I can also look at the other lines that the other relationships that we can still have in this particular situation. Now I'm looking at this other situation here, and let's see how it is going to work out. Now I have also this relationship here. I have this one is CF and this one is FD. So I want you to find another relationship, which is now another investigation B, and just find out what is the relationship between. Let me start with the big one, FD. If I get FD and find the ratio with CF, and then I find also the relationship of FB and also with that is EF. What can you talk about these particular ratios? Now what I'm getting from these ratios is that if you find the ratio, now in this case here, the first one here is D over A gives you 1.932. If you find the relationship B over C, you get 1.932. What does it tell you? Now this is the concept of linear scale factor. So the linear scale factor comes in because, as you know, that this angle here, the angle here at the center is the same as the angle here. These are opposite angles here, direct opposite angles here. They are equal, and then this angle here is equal to the other angle on the other side. So these are similar. These are similar objects here. The triangles are similar. So we can now use that relationship of linear scale factor, which tells you that if you have been given one side of the triangle, you can also be in a position to get the other side of the triangle. For instance, if I was given CE, which is 4.264, I can easily use the linear scale factor here for me to get dB. So how do I use the linear scale factor? So if I want to get dB in this particular case, then I have to say that dB, my length of dB is equals to, then I can say dB is equals to, that is the small length, which is 4.264, then times the linear scale factor, which is 1.932, and this one will give you this length here, this length here. So let's see whether our length that we are going to get and the length that is going to be generated through the computer are going to be the same. So what I have obtained here is that when I multiply this one, this is to 3 decimal places here, I get 8.238. But when I get it through the accuracy of the computer, it has many decimal places, then you get 8.241. You can see they are very close. They are just very close to one another, which means that this relationship of the sides also gives you a linear scale factor. So those are the areas that you need to check when you are doing questions on internally intersecting chords, which are very, very important. So I want you to attempt the following question. Now I have two questions for us to answer. So I want us to find the length DE which is missing. Yeah, and remember we said for us to get DE, these are internally intersecting chords. We said we just have to get AE. If you multiply AE times EC is equals to, if you multiply DE, then times EB. That is the relationship, as simple as that. Then which means that we have AE, which is 3.195 times 5.85, which must be equal to DE, which is missing. We want DE, then times EB, which is 2.453. So we want DE. So if we want DE here, then we have to divide both sides by 2.453. So divide both sides by 2.453. So what is the answer? DE then is equals to, so I get 7.620. So DE is equals to 7.620. You see how easy it is when you have that relationship. Then how do I get DC? If you look at DC, I have been given HK. I've been given HK. And what did we say about it? We said that we can also have the relationship that is linear relationship. And we said that in this case, we can have a relationship here. That if we have, for instance, DE, we can use DE over AE, is equals to, that is EC, the other side over EB. Okay, we can have those particular sides. So which means that we need D, we need D, which means that in this case, what are we getting? We are getting the ratio. So where do we have to get the ratio? So the ratio, we can easily get the ratio by getting 5.85 over 2.453. So this gives you the linear scale factor. So when you get this ratio, you can use it with the HK for you to get these other corresponding sides, which is DC. So what is this ratio here? So I get 2.385. So this is my linear scale factor. So if this is the smaller side, for you to get the bigger side, you multiply the ratio times the smaller side. Okay, so the ratio being, so if I want DC, then is equals to the linear scale factor 2.385, then times the smaller side, which is 4.096. So this one gives me easily 9.769. So this side we are getting approximately 9.769. Now what we did before is that we verified, we tried to justify what we are getting and verifying what we are getting, and then it became true. So that is how you can solve this type of a problem. Then we move to the second part, externally intersecting chords. Now look at this second relationship here. Externally intersecting chords. So the chords we are talking about, the chords that intersects, they intersects outside, they extended. These are extended chords. These extended chords are called seconds. So we call them seconds. They pass through 2 points on the circle, to the outside part. So these are called seconds. Now look at the relationship that we have. I'm going to use A, B, and E. Now if I use AE, this is the relationship I want you to look at. AE, then I want to multiply AE times BE as my first part. Then the second part, I just want to multiply my DE times then CE. Then from here we can now start debating, what is happening. Is there any relationship here? So let's start. What is AE? AE now is from A to E, which is given as OQ, which is 10.832. So here we have 10.832, then multiplied by BE, which is RQ, which is 5.744. That is the first part. Now the second part here is that I'm talking about DE. DE is PQ, which is 12.117, then multiplied by TQ, which is 5.12. So what do we get in the two cases? Then this one will inform us our next step. Will it help us to continue with our exploration? Does it give us some insight so that we can still produce, we move to the next level? So that is the question that we are asking. Okay, from my calculation, AE times BE gives me 62.22 units. DE times CE gives me 62.04 units. Now look at the two. Even from our own investigation, due to the number of decimal places and some small errors that can occur even in my construction here, we can say that they are near one another. They are almost equivalent. There is almost equivalence here. So this relationship can be taken valid. It can be valid, and you can justify that the difference here is due to, it can be due to the construction error in measurement. So we can now categorically then say that we can then assume that particular difference or error that occurs between the two, and say here that AE times BE, then it is very close. It is very close to DE times CE, and that is the relationship. So where do people go wrong in this particular question? Because of the concept of internally intersecting circles or chords, some people just multiply the relationship that AB times BE is equals to DC times CE. That is wrong, as you can see from the relationship. If you try that, then it won't work. Even from the linear or similarity, when we are talking about similarity, it's that we are talking about the larger diagram over the smaller diagram. You see, the larger is AE, the smaller one is BE. But when we say AB is not similar to BE, because going to the BE is a triangle, and coming to AB it forms another object here. So that is the relationship that we should be having. So therefore, if I have these areas that we are now talking about, the A here multiplied by E, then you multiply by B times E, which is the same as this relationship here. You go to E, then you multiply T times E. That is how it happens. So can we do together the following question? Now this is the question here. I want you to find the length DE. Now the first thing that you are supposed to do when answering this question is to write the relationship. What is the relationship? We know that AE multiplied by BE is equals to DE multiplied by CE. When you have that, you are sorted. Now what is AE? AE here, you see, you have been given AB and you have been given BE. So AE is AB plus BE. So you must add this one together, these two together, for you to get AE first. You know, you have to get AE. So which comes to what? Which, when you add, you get 12.33. So you get AE is 12.331 times, what is BE? BE now is 5.896. 5.896 is equals to DE. DE is what we want. DE is what we want times CE, which is 5.673. So we want DE. So for us to get DE, then it will be you get 12.331 times 5.896. Then you divide both sides by 5.673. 5.673 using the relationship, then it will give you DE directly. Then what do we get? DE is equals to 12.82 centimeters. So that is how you can solve questions using this particular relationship. Now we move to the third relationship, where we are going to have a secant and a tangent meeting externally. Now let us deal with the third case here. We have a tangent and a secant. You can see the secant is coming to this point, and then we have a tangent. So there is something that we need to investigate here, that if we have a tangent and a secant, then we can investigate the following and see whether it applies. One, we are going to look at the relationship here as usual, which is AE multiplied by BE. That is the first thing. And secondly, because now the tangent is just a line, it has no any other relationship, we just say CE multiplied by itself. So we are going to square CE, you know, because just like multiplying itself by itself. Then what do we get here? So AE is the total of this, which is HL1, which is 12.99 times BE is 4.633. So we need to get that result, and then get 7.775 squared. So what do we get in the two cases? So when you multiply the two, that we have AE times BE, you get 60 60.18. When you square CE, you get 60.45. So we can talk about the errors that we talked about. So there is a difference, but we can call it a minimal difference. It is not exactly that it has to come to be exact, but it has to be closer. It is just closer to one another. That is the closest relationship we can get between a secant and a tangent. So in this case, even if there is that difference, then it is now a relationship that is proved. That now, if you use, we said, if you use many decimal places, then it will come close and close to one another. Then, with that closeness, with that small error, then we can still say, categorically say, that there is a relationship between now AE, we can say AE, you multiply by BE, then it should give you CE squared. That is how this one is obtained. Okay, CE squared. CE is the length, that length squared. As simple as that. It is as simple as that. Very simple and straightforward. So let us do the following question. So we shall find the length CD given that I have AD and I have BD. So what is the relationship that we talked about here? We said that if we have AD, that is AD times BD, then it should give you CD squared. Then what do we have? Then we have 12.46 times BD, which is 4.309, which should give you CD squared. So if you want to get CD, then it means you have to get the square root of 12.46 times 4.309. So what is the answer here? Then you get 7.327. Okay, that is CD. So we can also justify this. You can see even from the computer generated, there is justification 7.327. This one was more accurate. Okay, this one was more accurate. So we can now say that that relationship holds. That relationship holds. Okay, and for all the questions of this nature, just use that relationship. Finally, we are going to talk about tangents meeting externally. So in this case now, tangents which are meeting externally, we have AE as our tangent and we have BE as our tangent. You can see the tangent touches the circle at a point, only at a point, you know. So AE is tangent 1, BE is tangent 2. Now, what are the characteristics of tangents to make it so easy for you? Now, I have extended a line from the tangential point to the center of the circle, and from the tangential point to the center of the circle. Does it tell you about something? Now, if we just, let me get the angle at point B, you see the angle becomes 90 degrees. That is a great exploration. So, a radius from the tangential point makes an angle of 90 degrees. That is the rule. Let's try the other side. It also makes an angle of 90. So that is a basic rule. So all the tangents, if you see a tangent line and you see a radius coming from the tangential point, then it makes an angle of 90 degrees. That is one. Now, what else about the tangents? When we are talking about these tangents, we can also talk about the distance. to the intersection point, which is 5.347, and the distance from here to the tangential point. You can see again the distance AE and BE are equal. So this is what we are getting simply in this relationship when we have tangent points, so that we have the distance AE is equals to the distance BE. That is very important, you see. And the angle OAE, this is the angle, is equals to 90 degrees. Very important. And the angle OBE, which is also equals to 90 degrees. Very important. Okay, very, very important. So if that is the case, then we can now categorically say that if we divide this part into two, then we are saying that the two triangles OAB and OBE are congruent triangles. So the triangle we have OAE, is the triangle OAE is equals to the triangle OBE. These are congruent triangles. Very important relationship. So you can see that OB2 is now our hypotenuse, and they are both right-angled triangle. So if you get this type of a question, then you have to know that this angle here, if this is angle of theta and this is the angle of theta, then this one will be alpha and the angles will be the same. Okay, and the angles will be the same. So that is the characteristic of externally tangent meeting externally, and it is a very important relationship such that when you get this question, don't be confused. Just know that this is a right angle. You know that this is your height, this is your hypotenuse, the length at the center, and then the two triangles are congruent. So thank you for today. I will continue with a more series of circle theorem. I'll go to circle theorem 3, where we are going to even find the area between 2 or 3 intersecting circles, and many more concepts on circles. So if you watch this video today, kindly like it and subscribe to it. Thank you so much for watching.